There are two operations that we can perform on vector fields that give us a better idea of some properties of given vector fields. These are called the divergence and the curl, and we'll discuss what each of these are measuring and how to compute them and some applications. First, let's start with divergence. Okay, divergence. So if you picture, let's say 2D, analogous three-dimensional definite. Actually, let's look at a 3D case because I'll give the definition in 3D. So we have some vector field, say F. Say we have something like this. Okay. And we take a given point. Let's say we take like this point here, maybe in red. And when we look at just the picture locally of what's going on near this red point here, there's a natural question we can ask. If this vector field is representing like velocity of a substance or a fluid or something, you could ask, well, how much is flowing in versus how much is flowing out at a given point? How much is flowing in and out at a given point? Right? And so normally what we think of is maybe you take a line or a curve through here, and then you look at how much is flowing in or out of this entire membrane, right? Think about this as like a permeable membrane or something. But now we're interested in just at a single point, and we want to say, okay, well, if this is representing like velocity of a fluid or something, how much is flowing in versus how much is flowing out? And this is called divergence. The answer is divergence. Divergence answers this. So let's look at a definition of the divergence. I'll give this definition in 3 dimensions, but it's an analogous definition in 2 or higher than 3. So let's let F be PQR here, this vector field PQR. Remember, P, Q, and R are all functions of X, Y, and Z. The divergence of F is, and we write this as div F. It's equal to, you take the partial derivative of P with respect to X plus the partial derivative of Q with respect to Y plus the partial derivative of R with respect to Z. So you can see if we like kind of order our functions P, Q, and R, and then order our variables X, Y, and Z, you take dp dx, dq dy, dr dz, and you sum up these partial derivatives. This gives you the divergence. And again, let's make a remark here. The divergence measures the quote-unquote outflowingness of a vector field. Okay, so this tells you like at a given point, is more flowing out or is more flowing in to this point? And if more is flowing out, we have a positive divergence. If more is flowing in, we have a negative divergence. If it's equal, we have no divergence, okay? And so we'll see some examples here. But first, let's unpack this definition a little more. Let's take a look at this definition a little more before we start doing some examples. The divergence of f was what we said to be del p del x plus del q del y plus del r del z. Now we know f is p q r, right? And if we think about the gradient operator, the gradient operator is a vector that can be expressed, or it can be expressed as a vector, partial derivative with respect to x, the partial derivative with respect to y, the partial derivative with respect to z, right? Because this is what the gradient does, is it takes the partial derivative in each component with respect to x, y, and z, respectively. If we think about the vector field f and the gradient operator, well, then we can change this. We can unpack this definition, or kind of repack this definition of a dot product between our gradient operator, del x, del y, del z, and our vector field, p, q, and r, right? This is, if you take the dot product here, well, you're applying ddx to p, you're applying ddy to q, and ddz to r, right? Again, here, this is a vector field, and this is an operator. Now, this is the dot product, and so we can use our notation here. Well, the gradient operator is given by this nabla here, and then dot our vector field, f. And so therefore, we have a more compact definition of the divergence. It's the gradient dot our vector field. And notice this gives us a scalar function, right? The divergence of a vector field is a scalar, right? And it's a scalar function until you plug in a specific point, and then it becomes just a scalar, right? Just a value, because this value will tell you the rate, like the comparison rate of outflowing versus inflowing of your vector field at this point. So let's see an example, or a few examples. Let's look at like a constant vector field. This will be our first example, constant vector fields. So let's look at f equals 1, 2. And let me come back here. So notice this now, this definition here, this applies to 2D or 3D, right? When I wrote the definition for the divergence, I gave the 3-dimensional analog. Now, the 2-dimensional analog would be to say, like, the divergence of f equals dp dx plus dq dy, right? Because now you would just have a 2-dimensional vector field f equals pq, and your gradient operator is only on the variables x and y because we have no z variable. So we can look at 2-dimensional vector fields as well. I just gave the definitions in 3 variables, but you can see this conclusion that we arrived at. The divergence is the gradient dot the vector field. This is intrinsic of dimension, right? This is for any dimension. Okay, and so, well, this is the constant vector field 1, 2, which means no matter where you're at on the plane, right, your vector is 1, 2. So it's over 1 unit up 2. And it's constant here. And intuitively, if the vector field is constant, you would say, okay, well, at a given point, there's another point where this point is the terminal point, but it's also the initial point for another vector. And both of these vectors are like the vector 1, 2. So intuitively, you would say, as much as flowing out at a given point, that's flowing in, right? Because it's even. It's an even flow, right? Nice Pearl Jam reference there. It's an even flow. But we can see this by calculating the divergence. Let's calculate the divergence of f. The divergence of f is the partial derivative. Well, just to kind of hammer in the idea that the gradient, or that the divergence is the gradient dot the vector field. This is partial derivative with respect to x of 1 plus partial derivative with respect to y of 2. And you can see this is 0 because 1 and 2 are both constant, right? And so the divergence being 0, this means equal amount flowing in and out at every point, right? And this makes sense that the divergence is 0 here. Let's see another example of a vector field with 0 divergence. And then we can calculate just an arbitrary one. So we can see how to plug in the divergence at a given point. Okay. Let's calculate the divergence of f of x equals negative y x. We've seen this vector field a few times now. It's a rotational vector field. Right, this picture is not going to be perfect, but the farther away you are from the origin, the larger the magnitude of the vectors. Right, this was our rotational vector field, negative y x. And we can calculate the divergence of f, which is the gradient dot the vector field. Well, this is going to be d dx negative y plus d dy of x. And you can see this is 0 because the derivative of y with respect to x is 0 and the derivative of x with respect to y is 0. And so this rotational vector field also has like a net 0 flow at every point. Now let's just calculate an arbitrary one here so we can see an example of something that ends up being non-zero. Let's find the divergence of f at the point 0 to negative 1, where f is e to the x I hat plus y z j hat minus y z squared k hat. So the divergence, remember, divergence is the gradient dot the vector field, which is partial derivative with respect to x of e to the x plus the partial derivative with respect to y of yz plus the partial derivative with respect to z of negative yz squared. This gives us, well, the derivative with respect to x of e to the x is e to the x. And then derivative with respect to y of yz is z. And the derivative with respect to z of negative yz squared is going to be minus 2yz. And now remember, so this means we have a non-zero divergence, which means it depends on the point we're at to calculate the divergence. And so we need to look at specific points to understand the divergence at those points. So we want now the divergence of f at 0 to negative 1. This is going to give us, well, we plug in 0 for x, we plug in negative 1 for z, right? So minus 1. And then we plug in minus 2 y is 2 and z is -1. And so this gives us, well, e to the 0 is 1, minus 1, and then it's minus a -4, so plus 4. And so we have divergence of 4. And that means at this particular point here, whoops, at this particular point, 0, 2, -1, the vector field is flowing out 4 times greater than it's flowing in, right? And so that's what this divergence is telling us. Okay, there is one quick application that I would like to discuss, and then we can talk about curl. We can talk about the other operation on vector fields that I would like to discuss today. And this is Gauss's law for magnetism. And this says if B is a magnetic field, then gradient dot B equals 0. This is what Gauss's law for magnetism states. It says if you have a magnetic field, then the gradient dot the vector representation of your magnetic field is 0. i.e., what does this mean now that we know what the divergence is? i.e., divergence of a magnetic field is 0. And so that's, in words, our conclusion. Therefore, the divergence of a magnetic field is always 0. And so what you can do is you can ask certain questions like, okay, well, can a certain vector field represent a magnetic field? And the answer to this question is now a lot easier because all we have to do is calculate the divergence. So let's see an example of this application. Can f of xy equals x squared y, comma y minus xy squared represent a magnetic field? And so the question is very easy to answer once we know that the divergence of a magnetic field must be 0. And so let's calculate the divergence of f. This is, again, gradient dot f, which is partial derivative with respect to x of the first component plus the partial derivative with respect to y of the second component. Calculating these partial derivatives, we're going to get 2xy plus, and then partial derivative with respect to y is going to be 1 minus 2xy. You can see we get cancellation here and here, but what we're left with is 1. This is clearly never 0, so the answer is no. This given vector field cannot represent a magnetic field because it does not have net zero divergence. Okay. Let's now then discuss the next vector, or the next operation of vector fields that we're interested in. Notice we've now thoroughly discussed divergence. We want to talk about curl now. So let's give some intuition of what the curl is going to calculate for us. The curl of a vector field. What the curl does is it measures the tendency of rotation of a vector field about an axis or a pole, right? And so you know, we've seen plenty of examples of vector fields that don't really exhibit any sort of rotation to them. You know, we have examples of vector fields with no rotation, where, you know, a perfect example is a constant vector field. There's no sort of rotation going on here. Everything is purely directed linearly, right, for a constant vector field. But we've seen ones that do exhibit rotation, such as negative yx, that, you know, was a good kind of a good template for indicating like wind speeds in a hurricane or something like this. You know, we've seen ones that like about this, some like pole in here, this axis, you know, there's a lot of rotation about this. And what the curl is going to calculate is the tendency of this. And the magnitude of the curl is going to tell you how fast things are rotating, right? And so, you know, then there's some vector fields that it may not be so black and white. It might not be like no rotation versus rotation. It might be like some rotation or increased rotation when you plug in these points and less rotation when you plug in these points or something like this. You know, a perfect example would to be like if you have, so let's just draw on the next page really quickly. Like if you were to have a vector field with like an asymptote or something, and so the vectors were coming in like this, you know, maybe behaving like this in some way, right? You can see as you approach the asymptote, there's really no rotation going on, but as you're farther away, you know, there is some rotation going on here, right? And so you can look at the curl at certain points, meaning like, you know, here there's a lot more rotation going on, whereas down the road here it's quite linear. There's not much rotation going on. And so the curl can vary, right? It doesn't have to be like one, it's not a constant for every vector field. And so intuitively, this is what the curl's doing, is it's measuring the tendency of rotation about an axis. And let's see the definition now. So let's let F be our vector field again. Let's let this be P, Q, R here. The curl of F is, and we write this as curl of F, is defined to be, now it's not fun to memorize here, so you have dr dy minus dq dz I hat plus dp dz minus dr dx j hat plus dq dx minus dp dy k hat. And so notice, one thing you may notice right away is that the curl is a vector field. Curl of a vector field is a vector field. So when you calculate the curl of a vector field, it gives you a vector. And at each point, you can calculate this vector. And depending on this vector is what tells you this tendency of rotation. What vector do we get, right? That's the next question is, okay, well then what vector are we going to get here? Well, let's look at this expression for the curl a little more here. We have all these partial derivatives, and we have these functions p, q, and r. And this looks pretty similar to me with, what this almost looks like is 2 by 2 determinants for each component, because it's like something minus something I hat plus something minus something j hat plus something minus something k hat, which reminds me of the cross product a little bit. And if you feel the same way, you're not mistaken. If we set up, again, we have our operator, nabla, that's the gradient operator, ddx, ddy, dz, and then we have our function, or our vector field, excuse me, f is pqr. Well, then the divergence was the gradient dot f. Let's see what the gradient cross f gives us. This is I, j, k. And then we'd have ddx, ddy, ddz, and then we would have p, q, and r for the third row. Now, let's calculate the determinant of this 3 by 3 matrix. So we have dr, dy, right, because that's this first piece here, and then minus dq, dz, right? So minus dq, dz, I hat, and then minus dr, dx, minus dp, dz, j hat, plus, for the third one, we have dq dx minus del p del y k hat. So the k hat's off the screen there, right? And then you compare, well, I could distribute this negative, so it would become minus dr dx plus dp dz, and you can see that's exactly what we get. We get that the curl of f is identical to taking the gradient operator and crossing it with our vector field f. So therefore, the curl of a vector field is the gradient cross f. And remember, when you take the cross product, you get something that is perpendicular to both entries. What this means is when you are looking at a vector field and you calculate the curl is a vector that's orthogonal to your current vector field. So let me erase this rotation here. So this would come like up, straight up. And the magnitude of this vector tells you the speed of rotation. And so remember, curl is a vector field. Magnitude, and so maybe I'll write actually the magnitude of the curl of a vector field. This gives us the speed of rotation. And so if this vector is very small, it's not fast. Relatively, it's not that fast of rotation, but if it's a larger vector, then your rotation is much faster. And so this is what the curl is telling us. It's measuring the tendency of rotation and then also telling us the speed of rotation once we take the magnitude here. And so again, this now works in 3D and 2D. I've discussed curl in 3 dimensions. Well, the curl in 2D, well, you don't really have cross product in 2D, so because you don't have a third dimension. But by definition, if f is p, q, by definition, the curl of f is defined to be just del q del x minus del p del y k hat, right? And so you have some vector field in 2 dimensions doing whatever, right? And then the curl sticks straight up because this k hat here you can see would be in the z direction. Alrighty. So let's do a quick example to calculate curl. Let's find the curl. So here's an example. Find the curl of f equals x squared z e to the y plus xz and xyz. Okay, and so calculating the curl, we don't need to remember that tedious formula. What we do need to remember is that the curl is the gradient cross the vector field. And this gives us I, j, k. Partial with respect to x, partial y, partial z, and then our vector field. So we have x squared z e to the y plus xz, and then x, y, z. Okay. Now let's calculate the curl. Well, the first piece, right? How do you take determinant? You start in the top left. So we have an I hat, but then you block out the row and column and you take the resulting 2 by 2 determinant. And so this 2 by 2 determinant is, so I'll write it out. Let's just write this out the long way. So this is partial with respect to y of x, y, z minus the partial with respect to z of e to the y plus x, z. And then this whole thing is I hat minus, then for j hat, we take j hat, delete the row and column that it belongs to, and then take the resulting 2 by 2 determinant. And if we do that, we're going to get the partial derivative with respect to x of x, y, z minus the partial derivative with respect to z of x squared z. And this is j hat, right? And then I'll write k hat up here. So plus k hat. You take k hat, delete the row and column that it belongs to, and look at the resulting 2 by 2 determinant, which is going to be the partial derivative with respect to x of e to the y plus xz minus, so I'm out of room, this is pretty sloppy here, I apologize. So plus d dx e to the y plus xz minus d dy x squared z k hat, right? And so now we can calculate what these partial derivatives are, and then we get our vector, our curl vector field. And so the partial derivative with respect to y of xyz is xz. So we have xz minus ddz of e to the y plus xz, which is x. So xz minus x I hat minus, for j, we have derivative with respect to x of xyz, which is going to be yz minus derivative with respect to z of x squared z is going to be x squared, so yz minus x squared j hat, and then plus for k hat, we have derivative with respect to x of e to the y plus xz. That derivative is just z. And then d dy of x squared z is 0 since there's no y there, so minus 0 k hat. And that means, therefore, our curl of f is the vector field xz minus x, x squared minus yz, and z. Notice here you may be saying I messed up a negative, but I didn't because I'm distributing this negative out front, which flips the signs there. Okay, so the curl measures the tendency of rotation, right? And so now for this given vector field, we have a formula that calculates this. It's now variable, right? It depends on where you're at in the XYZ space. And so you plug in a point and then it tells you, like the vector that indicates this rotation. Now, the curl is a vector field, right? We've said that. Curl of F is a vector field. Which means we can take the divergence of a vector field. So we can take divergence. Let's calculate the divergence of the curl of F, right? Well, this is going to be the divergence of, let's just use the long-winded definition of divergence here, and I'll use our subscript notation. So it's Ry minus QZ I hat minus PZ minus Rx J hat, right? Again, this is partial derivative notation. And then plus Qx minus Py K hat. Well, taking the divergence means we take the derivative with respect to x of the first piece, the derivative with respect to y of the second piece, and the derivative with respect to z of the third piece. And so this becomes Ryx minus QZX, and then minus PZY plus RXY plus QXZ minus PYZ. But remember that mixed partials are equal, and so we get cancellation. We know that RYX is equal to RXY. We know that QXZ is equal to QZX, and we know that PYZ is equal to PZY here. And so I messed up a negative. This should be plus. So this one is plus, and this one is minus. Apologies. So that's minus. And so we get this all cancels, and we get 0. And this gives us the following theorem, that the divergence of the curl of a vector field is always 0. And we can use this theorem to understand when a vector field is going to be the curl of another vector field. And so let's look at an example here. Let's show that F equals e to the x I hat plus yz j hat plus e to the z squared k hat. Let's show that this is not the curl of another vector field, i.e., we want to show that WTS is want to show that there does not exist some vector field G such that the curl of G is equal to F. And how do we do this? Well, what we do is we look at the divergence of F. We need to calculate the divergence of F. Because the divergence of F, so say if this G exists, then the divergence of F should be 0, since you would have the divergence of F is the divergence of the curl of G. And we know the divergence of the curl should always be 0. So let's calculate the divergence of f. And if it is 0, that means this G can exist. If it's not 0, then this cannot be the curl of some other vector field. So we have, let's calculate the divergence. So we have partial derivative, right? What's the divergence? It's the gradient dot f, which is partial derivative with respect to x of e to the x plus partial derivative with respect to y of yz plus the partial derivative with respect to z of xz squared. This is e to the x plus z plus 2xz. And notice this can never be 0 because e to the x can never be 0. This is not 0, implies g does not exist. So that means that this vector field cannot be the curl of another vector field. Okay, and now the last property I want to discuss is the following theorem, and I'd like to leave the proof to the watcher. So it's not too tough to prove, and it's good if you can prove this. I think you have a pretty good understanding of what's going on here. And so it's f is conservative. F is a conservative vector field if and only if curl of f is 0. And so the proof, I'm going to leave it to you, but here's a hint. Use the cross partials property of conservative vector fields. Okay, and so try to prove this yourself and see if you can understand why f being conservative means the curl is 0 and why the curl being 0 means that f is conservative. And this concludes everything I wanted to discuss about the divergence and curl. These are two very useful operations that we can perform on vector fields to obtain much information about said vector fields. Now, what we're going to discuss is surface integrals. We discussed line integrals. There were scalar and vector line integrals. Well, now we're equipped to discussing surface integrals. So there are scalar surface integrals and vector surface integrals as well. And it's a pretty, in my opinion, it's one of the more involved subjects of multivariable calculus and vector calculus. We'll need a lot of time to get some background information together and also to construct these integrals. And so that's where we're going to go from here. In the next video, we'll discuss surface integrals and how to compute them and what they're computing.